At the lowest level of computation, there are no objects, classes, or types. The physical substrate consists entirely of transistors shifting between voltage states. All hardware data is binary numbers in sequential memory cells, identified by base 16 hex addresses. The CPU executes primitive instructions like load, store, add, and compare, rewriting these binary states. Python objects are highly orchestrated memory layouts, spanning multiple addresses within this grid. Python functions as an elaborate set of rules mapped over these raw memory arrays, simulating object-oriented behaviors on top of electrical voltage states. This stack diagram illustrates the layers required to bridge physical hardware and high-level code. A massive program written in C executes every line of your Python code. This program is the CPython interpreter, the reference implementation of the language. Because the interpreter is a C program, every Python variable is governed by C's strict rules of memory management and structs. A struct is a composite data type in C that groups together different variables in contiguous memory. To understand dynamic typing and runtime behavior, we have to analyze the exact C memory structures that dictate state transitions under the hood. The flexibility of high-level Python code results from statically compiled C structures interacting through carefully managed memory pointers. This code block displays the foundational structure called PyObject. In Python's Python, every single object begins with this exact underlying structure. This memory schematic maps the C code directly to our RAM grid. When a Python object is created, the C compiler allocates a contiguous block of memory specifically for these fields. The first memory segment is the reference count, or OB rough count. This integer tracks exactly how many variables currently point to this object. This field dictates garbage collection, the automatic memory management feature that deletes objects when this count reaches 0. The second segment is obtype. This is a raw memory pointer, a variable storing the physical address of another location in memory, directing the CPU exactly where to look next. For a Python string containing the word hello, the structure is populated. The reference count tracks usage, the type pointer dictates behavior, and the actual string data is appended at the very end of the struct. An object in Python is a data payload chained to the rules of the interpreter by a single memory pointer to its type. The obtype pointer directs the CPU to a separate location in memory, a PyTypeObject structure. This is the physical reality of a Python class. This PyTypeObject serves as a metadata descriptor. Fields like TP_name identify it as a string, while TP_basic_size provides the memory footprint required to allocate instances of this type. The bulk of a class definition in CPython is a table of C function pointers. These fields dictate how the object behaves during arithmetic, string representations, and comparisons. When calling a method on an object, the interpreter rides the obtype pointer to this structure, locates the function table, and executes the C code. Placing the simple PyObject block and the complex PyTypeObject block side by side reveals an architectural paradox inherent in Python's design. Every single object must have an obtype pointer directing it to a valid type structure. Because classes are treated as first-class objects in Python, the type structure itself must also be an object. This means the type structure must contain its own obtype pointer, creating a chicken and egg scenario for memory allocation. If the CPython interpreter attempted to allocate these interdependent structures dynamically at runtime, it would trigger an infinite recursive loop and instantly crash. CPython avoids this crash by bootstrapping the core objects before the interpreter ever executes a single line of Python code. In the CPython source file objects typeobject.c, these foundational types are explicitly defined as static variables. Both the base object type and the type object itself are hard-coded as global C variables, baked directly into the interpreter's compiled binary. When the Python executable boots, these memory spaces already exist. The interpreter manually splices the memory pointers together during initialization. To satisfy the requirement that the type object has a type, the interpreter points the type struct's obtype pointer precisely at its own memory address. The foundational architecture of Python relies on this hard-coded infinite loop mapped in memory. This split screen shows a Python terminal and the corresponding CPU instruction. When you check the type of an integer, the hardware executes a straightforward translation. The interpreter locates the integer in RAM, offsets to the ob type pointer, and returns the physical address found there. When asking for the type of type, the CPU traces the offset, hits the self-referential pointer, loops back to that exact address, and returns a match. Python operates as an architecture of memory blocks, type descriptors, and function tables working in tandem. Mastering any complex system, from OS kernels to neural networks, requires recognizing that programming is the design of controlled state transitions within structured memory.